Welcome to the chapter on advanced mechanical design. In this chapter, we will delve into some advanced topics that are crucial for understanding and solving complex engineering problems. In this chapter, we will explore finite element analysis, dynamic analysis, and vibration analysis in detail. Finite element analysis, or FEA, is a computational technique used to approximate the behavior of engineering structures under various conditions. It subdivides a large problem into smaller, simpler parts called finite elements. The results from these elements are then assembled to give an overall solution. The basic concepts in finite element analysis include nodes and elements, meshing, and boundary conditions. Nodes and elements refer to the division of the structure into small pieces connected at specific points. Meshing is the process of dividing the structure into these elements. Boundary conditions are constraints applied to the model to simulate real-world conditions. The fundamental equation in finite element analysis for static analysis is derived from the equilibrium of forces. The equation is K U equals F, where K is the stiffness matrix, U is the displacement vector, and F is the force vector. Consider a simple cantilever beam subjected to a point load at the free end. The steps in finite element analysis would include modeling the geometry, meshing the beam into finite elements, applying boundary conditions by fixing one end of the beam, applying the point load at the free end, and solving to compute the displacements and stresses. Dynamic analysis deals with structures subjected to time-dependent loads. It is essential for understanding how structures respond to varying forces, such as vibrations, impacts, and other dynamic effects. The basic concepts in dynamic analysis include the mass matrix, damping matrix, and stiffness matrix. The mass matrix represents the distribution of mass in the structure. The damping matrix represents energy dissipation mechanisms. The stiffness matrix represents the rigidity of the structure. The equation of motion for a dynamic system can be written as mass times acceleration plus damping times velocity plus stiffness times displacement equals the force that varies with time. In this equation, the mass matrix is represented by m, the damping matrix by c, the stiffness matrix by k, the displacement is given by the vector u, and the time-dependent force is represented by f of t. Let's consider a single degree of freedom system, like a mass spring damper system. The equation of motion is mass times acceleration plus damping times velocity plus stiffness times displacement equals the external force as a function of time. In this equation, m represents the mass, c is the damping coefficient, k is the stiffness, u is the displacement, and f of t is the external force. Vibration analysis is a subset of dynamic analysis focused on the oscillatory motion of structures. It is crucial for designing structures that can withstand or avoid resonant frequencies. The basic concepts in vibration analysis include natural frequency, mode shapes, and damping. Natural frequency is the frequency at which a system naturally oscillates. Mode shapes are the shapes that a structure assumes at a particular natural frequency. Damping is the mechanism by which energy is dissipated in a vibrating system. The natural frequencies and mode shapes are found by solving the eigenvalue problem. It's the stiffness matrix minus the natural frequency squared times the mass matrix, all multiplied by the mode shape vector, and that equals 0. In this formula, omega is the natural frequency, k is the stiffness matrix, m is the mass matrix, and the mode shape is represented by the vector u. Consider a simply supported beam. To find its natural frequencies and mode shapes, we solve the eigenvalue problem, k chord m, u equals 0. By solving this, we can determine the frequencies at which the beam will resonate and the corresponding mode shapes. Understanding finite element analysis, dynamic analysis, and vibration analysis is essential for advanced mechanical design. These techniques allow engineers to predict how structures will behave under various conditions, ensuring safety and reliability in engineering applications.